people?
Okay, so I'm Gavin, work at Collab. Sometimes I'm a software engineer and protocol guy, other times some other things. But today I'm pretty jazzed to talk to you guys about sound. So the fact that this is the theme is just awesome, the fact that I'm up here. So my personal love in life is sound. Like I personally experience the world in an acoustic, sonic way. And so this is going to be my attempt to weave through my experience of life with sound and tie it into some of the deeper truths and experiences that I've had in the world, but also relate that to what you guys do on kind of an everyday basis and give you guys maybe just a different perspective on sound. And so sound isn't necessarily what you think it is. So what is it then? So this is Om. And so many places around the world have different, many traditions have different thoughts about sound. So the Buddhists have Om. There is this perpetual sound that propagates everything. In the Vedic texts, they have, there was Brahman originally, he was with the word, and there's this sound. Later on you have the Christians, and again, I don't describe any of these philosophies, but you have the Christians who have, in the beginning was the word, and was the word, and blah, blah, blah. And then if you want to go to physics, we're just talking about it, you have their concept of Big Bang, or vibration of strings, but either way, there's this, there's also a joke of like, Richard Feynman, if you remember him, when he won the Nobel Prize, he gave recalled a story that his first teacher relayed to him. He was asking, he asked Richard, he goes, Richard, do you want to know why the mass of every electron is the same in the universe? And Richard's like, well, why is that? And he goes, because it's the same electron. How? There's this like deeper thing going on that really we're kind of wondering about. But anyways, it's captured in this symbol, at least for our purposes. But really, what does this mean? So let's start with giving you guys we're going to relate sound to shape first. And so you guys might have seen cymatics. Let me fast forward and do a little video here for you. So just pouring sand on a plate here. You can kind of see some patterns start to form based on the frequency you play. You can just watch that change shape as the sound changes. Okay, so that's the gist of cymatics. But what it really is for our purposes is you get yourself a flat metal plate and you pour some sand on it or something that'll move quite easily, and you play a frequency through it. And so as you increase the frequency moving through the plate, you get these increasingly beautiful patterns. Yeah, right? It's like just stunning. But this is 2 dimensions, and it's kind of like, well, what's the significance of this? We'll get there. So now, imagine this is a complex pattern. Now imagine you have a very simple pattern, and that's kind of the key in this top left form. But imagine if you just wrapped that around a block. You kind of have this like 3rd-dimensional view of this pattern. Well, there's this cathedral in Scotland called the Rosslyn Cathedral. It's known for its stonework. But all around the top, you'll notice they have these like blue little boxes that we've drawn. And in modern culture, they kind of wondered what this meant. Well, there's I think it was a British father and son. The father was a code cracker and a mathematician and also a pianist. And then his son was a composer also. And they realized that there was this statue that was actually telling you, hey, this is actually how you play this sound. So if you move around this cathedral, they decoded this and ended up creating a piece of music from it, but they realized that this was actually, the geometry around the church was actually this composition. And so what's particularly interesting for the purposes of this is that the architects encoded sound in the geometry of this building. And so that is kind of our dive in. We related sound and shape. So let's take a look at geometry. We're going to start with 2-dimensional geometry initially. So, hold on, I got to pull something up on my hand back. We're going to play some sounds because this is about sound. Okay, so if you guys remember the basic shapes here, we have triangle, square, circle, and hexagon. But if we just take the degrees of these shapes and convert degrees 1 to 1 to a frequency, or hertz, these things have a shape. So you could say instead of 180 degrees, we're going to look at 180 hertz. So here's what this thing sounds like. This is a triangle. Okay. This is our circle square. And this is our hexagon. Okay, how can we go together? Okay, kind of sounds nice. Then we have the pentagon and the octagon. I won't go higher, just because it's a little hard on the ears. And then we have the seven-sided heptagon. Love this shape. Okay, so these, they're all kind of nice sound, but what happens when you play these things together is where this starts to get really interesting. So here's when you play some of these together, and we're just going to go through an ascending scale. All right, okay. All right. What you're actually getting here from just the sound of these two-dimensional shapes is an F-sharp major chord. Just 1-to-1 degrees to hertz. That's pretty neat. Okay. Okay, but now there's something else interesting here with these shapes, and this will come in later. But notice that each one of the points on the surfaces of this, except this is an interesting shape, each one of these points is equidistant from the others on the surface. We'll come back to that. But this is the response I usually get, right? This is my attempt to combine all this shit into like talk. So people are like, oh, cool, neat coincidence. All right, well, let's move from 2 dimensions into 3 dimensions. Anything that has some particular depth should be able to be triangulated from a couple of sources. So let's move into the platonic solids. Do you guys remember these things? Other neat shapes. 3D geometry. Maybe it makes reality, maybe it doesn't. Who knows? Let's go. So, this is the tetrahedron and the octahedron. This is the hexahedron, or the cube. We all know this one. And then up there we have the icosahedron. I didn't probably go decahedron. We can get into that later. But anyways, again, these things have particular degrees. The degrees is just the sum of the angles and the shapes. Again, we've gone from 2 to 3D. But are you guys going to guess what happens when you play these sounds too?
Forward.
Yeah. Yes. And guess what? Oh shit! It's an F-sharp major chord. The exact same chord, just up a little bit. I didn't play them on this because it's a little intense to hear with this app. So if anybody's really good with sounds and things, I'd like to learn. But that's interesting. Same chord, just up an octave. But also to note. That each one of the platonic solids is contained in a sphere, and what's particularly interesting is that these points are again equidistant, and each point is the tangent point on the containing sphere. We'll see why that's interesting again. But again, this could just be another neat coincidence, right? Wow, we've got the same. Okay, so for those of you who are still skeptical, let's go find something else. Flower of life. So we just been in kind of mathematics and geometry land. I'm going to take you guys over into spirituality and different wisdom traditions from around the world land. Now, you might recognize this shape. This shape is of particular interest, and you find it all around the world. You find it in the temples in Egypt, in the pyramid. You find this in Greek temples. You find it in megaliths in Mesoamerica and South America. I could go in Australia. You find it in the caves of the Dogon tribe in Africa. We could just go on and on and on about where this shape is, but aside of seeing some neat geometry and the fact that there's a lot of harmony and symmetry in it, I'm going to take you guys down a spin about one way of perceiving this shape. So all we did is we're going to take the initial circle, because there's always one circle in the start, and then there's 6 circles around it, so we're going to take a look at this. So now if you just take these surrounding 6 circles and you sum the degrees, and you play those as a sound, what do you think happens?
Harmonic chord.
Oh man, this is goes on it. So yeah, again, we get F sharps, A sharps, and C sharps, and we get, again, another F sharp major chord. And so we have triangulation of a particular chord across a couple of different information systems. So now, we're going to be getting into things that are a little more concrete. So one thing to do that's useful here is to you probably see 7 interlocking circles, right? But there's a different way of perceiving the shape, and this is where putting on a different lens of dimensionality is really useful. This is good as designers too. Nice hygiene to have different lenses, right? So you can see these interlocking circles, but not just see it as 3D, right? So you can start to see how spheres pack and maybe how molecules might be a thing, or how things might come together in a particular shape. Okay, can I keep going? All right, so all that just related sonically, right? We just heard the sounds of those shapes. So it relates sonically, but what about geometrically? Because we want to triangulate some meaning here. So geometrically, in terms of the platonic solids, would be interesting to see. So how the hell does the flower of life actually relate both sonically and geometrically? Let's find out. The fruit of life. Okay, so what the hell is the fruit of life? The fruit of life emerges from the flower of life, of course, right? There's fruit. But the flower of life is, you'll notice it's 3 circles across effectively. We got the center circle and this circle. So let's put those together over here. And then the fruit of life is extending each one of these circles by 1 circle. And so this shape here is what we're going to look at. And this shape was so sacred that in the days of like the Pythagorean cult way back when, they would actually like cut your throat on sight for talking about this shape, because they would talk. The rumor had it was that this shape contained all of reality in it. Let's see. Right? All right, so we're going to just work with this shape on the right. So all you do here is just connect the centers of these circles, and you get a particular shape. So this is what happens when you do that. And so now we're just going to look at this shape. Okay, so what's interesting about this, aside of the just absurd number of lines, and again, symmetry, is that this shape contains every one of the platonic solids that we just saw in 2 and 3 dimensions, or 2-dimensional shapes and platonic solids in 3D. But each one of the platonic solids is nested. So we have a cube within a cube, which is nice. We have the tetrahedron inside of a tetrahedron. We have the octahedron inside of the octahedron. We have the icosahedron inside of the icosahedron. Shit, this for a while. And then we have the dodecahedron, magic shape. We should just talk about geometry at some point. But so that's all going on inside of there. And what this is effectively hinting at is that maybe there's a nesting that's taking place. Things are scaled and nesting. And so what we've done is we've looked at geometry in 2 dimensions and 3 dimensions. We took a totally different path and took a look at some spiritual traditions in terms of flower of life and fruit of life. But here's where I usually just goes off the rails and people go, well, hey, do you have anything real? Like, what the hell's the point of all this? Let's go there. Elements are pretty tangible for most people, aside of the fact that they're just energy, so let's look there. Atoms. All right, meet silicon. This is in everybody's pocket. It's everywhere. And this is how most people are introduced to it in their high school textbook, right? It's 2 dimensions, and it's flat on a piece of paper. And of particular interest is note the electrons. All the electrons are naturally going to be equidistant because they have the same charge. So they repel each other in the same way. So they're always going to separate themselves at equal distances. So the valence electrons on the outside are, of course, equidistant. But electrons don't really look like this. They look kind of more like this. They're like spheres packed in spheres. They're kind of in these shells of probabilities. So electrons are probably more a little bit like this if you think about it. And so when you think about where electrons orient themselves, or how they find harmony within these shapes, and again, harmony matters. Otherwise, they fall to pieces. If you have 3 electrons in a sphere, they form a planar triangle. They have to because of how they repel each other. If there's 4, it's naturally going to form a tetrahedron. If there's 5, they form a trigonal dipyramid. It's a neat shape, seriously. And 6, you'd have an octahedron, and just so on and so on and so on. So, what does this mean? This shape is a sketch of one of the first models built by a guy named Dr. Robert Moon. Robert Moon was an American-born physicist and mathematician who led work on the Manhattan Project. And anyways, he was the first physicist in modern times to prove that effectively elements are just nested platonic solids. They have to be because of how electrons repel each other. And so he built a lot of these models. This is a model of one of his models. But in case This is not a pipe. Sorry, bad jokes are just going to be all day. But that's this shape. So Robert Moon, as one of the first guys who brought this into awareness, at least in this culture. But in terms of practicality, this is palladium. This is a drawing of how palladium actually structures itself. So you can see the nesting nature of palladium. You have the natural structure is a containing dodecahedron. Inside of that is an icosahedron. You can see the angles. Inside of that, you have an octahedron, and then sitting at the center is this cube. And so that is actually how palladium has to structure itself. So it's kind of interesting to see that we have that as a thing. But if you're thinking this is all modern and neat, remember Johannes Kepler, Scientific Revolution, planetary orbits, things like that? This was on the cover of one of his books. So he's talking about the structure of reality being nested platonic solids in the 16th century, 17th century. So that's, what? Okay. So anyways, let's just take this for what it is. Atoms have to be nested platonic solids because of their repulsive forces and their spherical contract to align in particular orbitals. So if atoms make things, then they're part of chemistry. So does chemistry also contain geometry? For those of you who know, yes, I'm getting a smile right here. Yes, they do. Meet caffeine. Pentagon, hexagon. If you look at benzenes, they have the same pentagon, hexagon structure. But geometry and chemistry is just like, it's just what it is. Because if you change the structure of a particular molecule, you get a particularly different outcome. And again, if you think back to where we started this thing, when you play sound through a plate and the shape or the structure of that form changes, just start to think about what happens if you play a sound through something like this. Does the shape or form start to change? I know my bet. Maybe it does, maybe it doesn't. But this is caffeine, and again, structure. And so this is then how most people think of water, kind of like two-dimensional, right? You have H2O. And you think about how these things structure themselves. We've kind of been taught to think in two dimensions. But really, molecules don't exist in isolation, and they don't exist in the second dimension. So this is a little more accurate way to think about water. These loosely held bonds in this structure, and based upon what's going on in the water's environment, these bonds are a little bit different, the structure can be different. But water forms kind of this three-dimensional lattice. And as you start to compose more complex things, you get to things like this. This is just this is graphene. This is called a buckyball, but Buckminster Fuller. That's why it shows it for this. But yeah, you can start to kind of think about what the sum of this actually is. You've got a bunch of pentagons and hexagons. Okay. So now, this is going somewhere. It's like, maybe you've been duped because you've just seen a bunch of my drawings on the screen, right? Like this is just a bunch of BS. So, okay. Wow. This is the world's first close-up photo, and this is in 2009. This is physicists in Toulouse, and I think it's CNRS. It's France's National Physics Research Institute. But what this is actually the world's first close-up photograph of a graphene molecule. So it's a close-up photograph of this. But you see these just geometries here, right? You see these hexagons. And it kind of looks reminiscent, if you think about it. We have this center circle, and we have 6 surrounding circles. We've seen that form before. And so what happens when you put spheres next to each other in a vacuum is they stay spheres. It's like if you have a bunch of bubbles next to each other, they stay bubbles. But if you apply atmospheric pressure and you start pressing them in, you actually get these intersects. These straight lines form at the point of intersection. And so if you recognize this shape, that kind of is the flower of life, these same intersections. This was actually the cover of a chemistry book in 1912 from another person who has an interesting background. But, so you start to see what happens. And so if you just kind of apply that, you see the same form. So that's kind of that's a whoa moment. Where we took a sound of frequency, moved it through 2 dimensions and 3 dimensions, plumbed that sound from one wisdom tradition through another, and we looked at how it went from effectively atomic structure through chemical structure. And so that hopefully is kind of a whoa moment. If it's not, find me after this talk, we can keep talking. But this stuff seems a little bit odd and a little bit esoteric, but this is in the last year. This is really useful. And most of the world just isn't taught this stuff. So anyhow, so what's this mean? So yeah, atomic structure, molecular chemistry. Like that, there's more applications of this. You'd be very surprised where they are. Because speaking of the atomic bomb, right, Robert Moon stuff, in order to detonate the first atomic bombs, they actually had to use icosahedron shapes because that's the only way you could have a charge compression enough to split the atoms and do the thing. So these things are very useful, very powerful in a number of ways. But all that said, you have. Make noise for Adam's laugh. We tend to think of sound as this, in this, like, we've been taught to think of it in a naive way, right? You have this point and then you have sound moving in this wave as time goes forward. But in truth, sound is this, it's this like informationally dense medium. You have this sonic event that doesn't, it propagates as a sphere through space. And it contains a shitload of information, as we just saw. More than just a sound, there's a lot of harmony and balance and things going on in any sound. And so what I'd like to just imprint into this field is the idea that sound is an extremely robust design material. It scales infinitely. We can go inside of atoms or we can go way beyond you. And it's something that's universal in its experience. And so when you think about triangles or squares or pentagons or hexagons or whatever, we can think about harmony as a sound and a shape. If the shapes weren't harmonic and if electrons weren't harmonic in their positionings, kind of atoms would just, they'd shape themselves to pieces. There'd be no balance. And similarly with sound, we have the same thing. So we kind of start to think of harmony in a new way. It's not just acoustic, but it's also visual. And as creators, we can be working with these things. So where does this go? So the feeling of resolution is something that we'll finish with. The fact that you can hear things that make you feel a particular way should be of interest, because you can think about, okay, I could teach a person, or you could teach a person how to listen to a piece of music so that they appreciate, when a particular instrument comes in, or how a chord progression works, or any of these things. And that's something that can be trained, but something that can't be trained and that is universal, that somebody of any age understands, is just the way sound cultivates a particular feeling. And so that feeling of resolution is something that is innate within every human. And so that kind of implies to me that there's something more going on when you are working with sound that can harmonize an individual to an experience that you're wanting to craft. And so anyways, that innate aspect is something that I think is pretty deep, and connecting that depth to now some of the actual geometry and physics of, just the material world is hopefully been interesting. So, sound hopefully is a little bit more than you thought. And that's about it. Thanks.